So I hope that the three regions, the mixed region, including the saturated liquid and saturated vapor states, the superheated region and the compressed liquid regions, they are clear to you.
Yes, sir.
All right. If they are clear to you, these tables are for water. In case you have to use the tables for refrigerant, they will follow the same guidelines. You will not find the table for compressed liquid for the refrigerant R134A because it is normally not needed. Um, you will use the approximation. And for the superheated, the tables under pressure, saturation temperature, under saturated refrigerant under temperature, and saturated refrigerant under pressure, these tables are all given at the end of the book. And you also have the PDF version of the tables with you. Now we'll move on towards the concept of ideal gas, and we'll try to see the ideal gas relationship. The ideal gas equation of state, it is an equation that relates pressure, temperature, and specific volume of a substance. And if you remember, you have ideal gas property tables for air, nitrogen, oxygen, hydrogen, and different gases. They are there at the end of the table and at the end of the book. And they follow this relationship, which is the simplest and best known equation of for substances which behave in an ideal manner. The equation is this, where pressure is inversely proportional to the specific volume and directly proportional to the temperature, provided R is the gas constant. Now, remember, in this equation, R is basically the gas constant, which would be different for different gases. R is a gas dependent constant. Sorry. R is a gas dependent constant. And why do I say it's a gas dependent constant? If we look at the units of R, it is, if I make R as the subject of the formula, I'll have P into specific volume divided by the temperature. P into specific volume is kilojoules per kg. You already know that. And temperature is in Kelvin. Whenever you are referring to the specific gas constant R, it would be expressed in terms of per unit mass. So whenever you are using the gas constant, it is expressed in terms of mass. For, let's say, any value of Kelvin, the amount of energy associated with 1 kg of oxygen would be different with regards to 1 kg of nitrogen. So different gases would have different R values. However, when you express R in terms of molar value, the relationship is this, where R is equivalent to Ru over molar mass. Ru over molar mass means that M molar mass multiplied by R would give you the value of Ru. And Ru is basically expressed in terms of, the only difference between R and Ru is that it is expressed in terms of kilojoules per kilomole per Kelvin. So the difference lies in the quantity for which you are expressing the energy. R is the energy associated energy, Ru is the energy associated with 1 kilomole of any gas, because 1 kilomole would have the same number of particles. So this Ru value is a universal value. It is same for all the gases, whereas R values are the values which vary for air, helium, argon, nitrogen, and so on and so forth. When they are expressed in terms of per unit mass, each gas would have different value. But when they are expressed in terms of kilomoles, each gas would have the same R value. Is it clear to you?
Yes, sir.
All right. So now we'll look into how we can convert this generic equation into the molar equation. So let's say you already know that mass of a substance is equivalent to uh, mass is equivalent to molar mass multiplied by the number of moles. This is something that is known to you from high school chemistry. And if I want, this is my equation, P specific volume equals to RT. And I know that specific volume is what? PV equals to PV over M equals to RT. I can express this equation as PV equals to MRT. Is this equation clear to you?
Yes, sir.
Now, if I replace over here M with molar mass and number of moles, I would have this equation PV equals to M N R T. Is this equation clear to you?
Yes, sir.
I have replaced the mass with Mn, molar mass multiplied with the number of moles. I hope this is clear to you.
Yes, sir.
All right. And in the last slide, you saw that M multiplied by gas constant is equivalent to universal gas constant. So I can replace this in this equation. I can replace PV equals to, instead of M and R, I can write RU N T. So I can write this equation PV equals to number of moles multiplied by RU multiplied by the temperature. This is another form of the same equation. Clear?
Yes, sir.
And one thing for your notice is that when you are expressing Ru, which is kilomoles based on per kilomole, you are multiplying it with the number of moles to cancel out each other. And so this is the expression where this is the generic equation we started with. Then we developed this equation PV equals to NRUT. And if I bring N on the other side, I would have V equals to RU into T. And V over N is nothing but the molar volume, which is written by small v having a dash on top of it. All right.
Yes, sir.
All right, great. And if I have constant mass, I can write the equation. If my mass is same, the equation would be written for two different states as this. P1 V1 over T1 equals to P2 V2 over T2, provided you are talking about fixed mass. Again, per unit mass, when you are expressing the properties, they are represented by small letters. When you are expressing per unit mole values, they are expressed by small letters having a dash on top of it. Now the question comes, can all the gases be assumed to behave in an ideal manner or ideal gas? The answer is that under low pressure and high temperature, or in other words, at low densities, your real gases behave as ideal gas. And for most of the applications, air normally behaves at low pressure, so you can assume air to be behaving as an ideal gas, and you can apply the relationship that has been discussed in this slide and the last slide. The question comes, can we assume water vapor to be an ideal gas? In order to study that, a graph was plotted in which the values of water vapors, which is vapors in superheated condition, were compared, the specific volume of vapors in superheat condition from the tables, the water tables were compared with the specific volume calculated using ideal gas relationship. And this is the data that was plotted. So you see the numbers written over here. The number indicates the error in the values. That means the difference water as calculated from the table or as calculated from the ideal gas relationship with the 76, 25.7, 16.7, 49.5, 7.4. It indicates that as long as your pressure is as long as your error is less than 1%, you can assume water vapors or superheated vapors to be behaving as ideal gas. 1%. Why? If you look at this point, this indicates error of 1%. This point indicates error of 1%. Again, this indicates error of 1%, and this indicates error of 1%. So when you combine the line, you see that this shaded region is the ideal gas region for water vapors. Water vapors behave as ideal gas as long as this error is less than 1%. And if you see for the line of 10 kilopascal, this 10 kilopascal line, this continues. I'll change the color so that it becomes more clearer to you. So if I draw this 10 kilopascal line, this is the 10 kilopascal, sorry, this is the 10 kilopascal line moving. And for this 10 kilopascal line or pressures less than 10 kilopascal, water behaves as ideal gas. However, in this region where you have a critical point, the pressures are very high, 100 kilopascal, 1 megapascal, 5 megapascal, 10, 20 megapascal. The error goes very high, up to 150%. So you cannot assume water to be an ideal gas at high pressures. Is this point clear to you?
Yes, sir.
All right. So as I've already mentioned that for 10 kilopascal pressure or below that, water vapors can be treated as ideal gas with error less than 1%. And at higher pressure, the ideal gas assumption is not acceptable as the error goes very high. And based on that, in air conditioning applications, water vapor can be assumed as ideal gas because the pressure is low. However, in steam power plants where the pressures are very high, you cannot apply the ideal gas relationship on water vapors. You'll have to rely on the steam tables, that is A4 to A7. These tables are to be consulted. Clear enough?
Yes, sir.
All right. Now we'll look at some of the examples to understand what we have learned, and you're going to help me out how to find out the properties. So let's say I have a rigid tank that contains 50 kg of saturated liquid water at 90 degrees. So I have saturated liquid water at 90 degrees centigrade. The mass of liquid is 50 kg. I have to determine the pressure in the tank and the volume of the tank. How would I determine that?
सर A4 टेबल पे
Very
उस
good.
पे
So,
सैचुरेशन
Gigi,
सैचुरेशन टेम्परेचर देखेंगे जिसमें 90 आ रहा हो.
no. Saturated liquid water at 90 degrees centigrade. You will directly go to table A4, read the reading against 90 degrees centigrade. 90 degrees तो है ही है. This is your condition. 90 degrees centigrade saturated liquid. Yes, your saturation temperature is also 90 degrees centigrade, but since the data is given in terms of uh, temperature, you will go to table A4 for 90 degrees centigrade. For 90 degrees centigrade, you will read the pressure against it. This would be the saturation pressure or the pressure of this line. This line would have the pressure of 70.183 kilopascal. So your tank would be at this pressure. Clear enough?
Yes, sir.
And what would be the volume of the tank? How would you calculate the volume of
Sir,
the tank?
50 multiplied by specific volume of saturated liquid,
Very
0.001036.
Very good. Very good. So you'll go to table A4, read the value of a specific volume of saturated liquid at 90 degrees centigrade, which is 0.001036 meters cube per kg, and you will multiply it by the mass of the liquid in the container, which is 50 kgs, and you will calculate the volume in the container. Clear enough?
Yes, sir.
All right, let's look at this example. I'm not showing you the examples of EES at the moment. How do you do it in EES software? Let's do it numerically using your notebooks and the tables given to you. So a mass of 200 gram of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascal. Determine the volume and the amount of energy transferred to the water vapors or to the water. How would you find it out? First, identify the table that you'll use.
Sir, A5.
Very good, table A5. And what property would you find out?
प्रेशर 100 किलो देखेंगे कि फर्स्ट कॉलम में होगा
100 किलो, राइट। 100 किलो पास्कल पे क्या चीज देखेंगे आप?
द पहले वॉल्यूम चेंज जो कि वी एफ जी के बराबर होगा मल्टीप्लाई
बिल्कुल,
बाय जो उसका मैथ जो भी उसने दिया हुआ है।
वेरी गुड।
उसके बाद उसने अमाउंट ऑफ एनर्जी पूछा तो हमारे पास पर किलोग्राम के लिहाज से वो दी होगी उसकी हीट ऑफ वेपराइजेशन।
हीट ऑफ वेपराइजेशन क्या होगी?
HFC
HFG, very good.
लेटेंट हीट स्पेसिफिक हीट ऑफ
So you
और
will
उसको
go
मल्टीप्लाई कर
to,
देंगे मैथ से।
very good. You will go to table A5. You will highlight this row, which is for 100 degrees and 100 kilopascal. You will read out the value of VF and VG. The difference would give you the change in specific volume. Then you will multiply it by the mass, which is given to you as 0.2 kg. And this would give you the change in volume. For energy transfer, you will go to enthalpy, not internal energy. We have already discussed that HFG is the latent heat of vaporization. It is the energy transferred to the liquid, saturated liquid, so that it moves to saturated vapor. HFG multiplied by the corresponding mass would give you the energy transfer to the water vapors. Clear enough?
यस सर
Yes, sir.
All right, great. So what I'll do is that I'll stop over here and we'll continue from the same point in the upcoming class. We'll look at few more numericals and try to utilize the tables to solve those numericals.